Hey everyone, welcome to the Chemical Bonding Introduction Lecture. So there are three different kinds of bonds that we're going to talk about in this class. And we've kind of already looked at one of them, not in a lot of detail, but ionic bonds. And ionic bonds are where you've got metals and nonmetals, and the metal essentially loses electrons, and the nonmetal essentially gains those electrons, and they bond together via that sort of electrostatic positive-negative attraction. So wherever there's a positive, it's surrounded by a negative, and that kind of holds things together. The other kind of bonds that we haven't really looked at in a lot of detail are metallic bonds. And metallic bonds are where you've got metals and metals. And they could be the same metal or they could be different metals. But essentially what you have is the metals lose an electron, and so they're positively charged. And where does that electron go? Well, it doesn't actually just surround the metal. It sort of forms a cloud around both of the metals here. In fact, we call this the electron sea. And the electron sea kind of holds everything together. In actual fact, that's why mirrors work, because that electron sea is what reflects the light back at you. And the third kind of bonds, which is what we're going to focus almost all our attention on today, are covalent bonds. And covalent bonds are what you get in molecules. And so molecules are what you get when you've got nonmetals and other nonmetals coming together. And in this case here, unlike in ionic bonds, where you get the sort of transfer from one side to the other and the electrostatic attractions hold them together, and in metallic bonds, where you essentially get these electron sea kind of holding the kernels of those metal ions together, in covalent bonds, the electrons actually are shared in between the atoms. So the electrons here are shared, and this line represents shared electron pairs. These bonds are a little bit harder to draw, so we're going to use what we call Lewis structures, and we're going to start off with Lewis dot symbols, and essentially each dot is going to represent a valence electron. And so remember, those valence electrons are the one on the outside of the molecule, or the outside of the atom at this point here, and it is almost always the exact same thing as the group number. So the group number, that is 1A through 8A for the main group elements, is almost exactly the same. And why is it not always the same? Well, helium's actually the top of group 8A, but it actually only has 2 valence electrons. So helium's the only exception here. And if we go ahead and we go across, say, the second period, we've got lithium and beryllium and boron and carbon at the top of groups 1, 2, 3, and 4, respectively. And so we write a single dot, 2 dots, 3 dots, and 4 dots around those elements. As we march across the period, the next element is nitrogen. It is in group 5. We actually put 5 dots around it, but notice actually the 5th one we pair. Oxygen is in group 6. We put 1, 2, 3, 4, 5, 6 dots around it. Notice we pair the 5th and the 6th one. And fluorine is in group 7, so the first 4 are unpaired. The next 3 are paired. And all the way at the other end of the group is neon. And neon actually has 8 around it. I probably shouldn't have paired them up like that, but I should have done 1, 2, 3, 4 individually, and then 5, 6, 7, 8 paired up. But notice that as we go across the period, the first half of the elements across each period are unpaired dots, and then as we go across the last half, right, we start to pair up those dots again. And what are they? So they are the valence electrons. So if we take a look at lithium, its electron configuration is 1s2, 2s1, and so that white dot there around the lithium is that valence electron. If we go to something like carbon, carbon is 1s2, 2s2, 2p2, and so those 4 electrons there, right, so those are the valence electrons are written as dots. And in the case of neon, right, so it is 1s2, and then actually all remaining electrons are valence, so 2s2, 2p6. So you can see the group number, right, is corresponding to the number of valence electrons, which is a really awesome kind of trick. So let's quickly discuss ionic compounds. So we know that metals are going to lose electrons, and they lose electrons to essentially expose a full inner core. And nonmetals are going to gain electrons, and they are going to gain, if I can spell gain, electrons, and they're basically going to fill the outer shell. Okay, this almost always exposes 8 electrons in the outer shell, which is where we get something called the octet rule from in both of these cases. So let's look at an example. So if we look at potassium and we look at chlorine, potassium's in group 1, chlorine's in group 7, so we're going to put 7 dots around it, and the potassium is going to go ahead and lose one valence electron, and the chlorine is going to gain one. In fact, you can almost think about this valence electron as basically being dragged over here on the other side. So now the potassium has no valence electrons left, and the chlorine right now gains an electron, so it is actually chloride here, so 6, 7, 8. And it's got a charge that's -1. Some people like to put this in square brackets. I don't think it matters too much. If you look at the electron configuration, let's see, potassium was based off an argon core and 4s1. Chlorine, let's see, that was based on a neon core, 3s2, 3p5. And so when the potassium loses an electron, now it is isoelectronic with argon. Okay, and then when chlorine gains an electron, it fills up that outer shell, so 3p5 becomes 3p6, and now actually this entire electron configuration is exactly the same as our friend argon. So we can see that ionic compounds are just going to gain and lose electrons, the individual atoms, until they look like the ions themselves are isoelectronic with those noble gases. That's almost always going to be exposing full outer shells with 8 electrons in.